So welcome back, GLS4OM students. I believe this is the last lesson in Unit 5, which were applications of derivatives. This is something completely new. We do not cover this in high school MCV at all. It's related rate problems, which will require us to use implicit differentiation to solve. And you're going to be solving some problem with regard to time. So no Euclid problems of the day. Here's the comic for the day. Maybe we'll come back to that once we do the lesson, because you'll find this much funnier after I teach you how to do related rate problems. All right, so related rate problems, how are we going to handle them? Just want to make sure that that's the thin marker. All right, so you're going to get at least two or more variables that are related. It could be volume, it could be profit. You're going to take the derivative of everything. The key here is with respect to time. Related rates are time related. So they might tell you something about how the volume is changing with respect to time and ask you to figure out how the height of something is changing with respect to time. How do you solve these problems? One, figure out what the objective function is. What are they talking about? Is it a volume? Is it an area? Then assign variables based on that particular formula. Again, once you set up that objective equation, you're going to then differentiate with respect to time. You're going to do d by dt of everything. If f is dependent upon more than one variable, you don't have to here write it as one variable. I don't. You can, but you don't really have to, as long as you're given information about d by dt. Don't substitute until you've computed the derivatives, because you'll run into an error, you'll lose a piece. Pythagorean theorem and similar triangles arise quite often in related rate problems. So if you see a triangle, then you know, am I using the Pythagorean theorem? I would use that one as long as I knew one of the sides was not going to change in length, or similar triangles otherwise. So let's look at the first problem. A 5-meter ladder is leaning against the wall. The bottom of the ladder is 1.5 meters from the wall at time 0, and it slides away from the wall at a rate of 0.8 meters per second. Find the velocity of the top of the ladder at time t. So let's say initially this is where we are. The ladder's up against the wall. It's 5 meters. What's going to happen is the foot of the ladder is going to slide this way, and the top of the ladder is going to start sliding down. They tell you at what rate this is. You're heading this way at 0.5 meters per second. This is coming down the wall, so I expect the rate to be negative. And now this is like, I'm going to call that the wall distance, and maybe this the base of the ladder distance. So then you're looking for a formula that will relate all of them. Take a look at what you have. You've got a triangle here. This side isn't changing, so it would make sense to use the Pythagorean theorem. So I'm going to suggest set up the Pythagorean theorem, then differentiate everything with respect to time. And what you're trying to find, this one is going to be the derivative of the base with respect to time. They want this one, the derivative of w. So again, set up the Pythagorean theorem, take the derivative with respect to time of all the pieces, and see if you have enough information to solve the problem. I'm going to pause just as a reminder or suggestion that you should actually try solving these. All right, so attempting to walk you through the solution. So the first thing I suggested you should do, I know there's a lot happening on this slide. Let's just focus on this a little bit. I said start with the Pythagorean theorem. So the Pythagorean theorem says that 5 squared should be equal to b squared plus w squared. And then I suggested take the derivative of all of these pieces with respect to time. So the derivative of a constant with respect to any variable is going to be 0. That's where the 0 came from. Here I'm going to have to use implicit differentiation. So the derivative of b squared with respect to itself is 2b times db by dt. Plus, if we take the derivative of w squared with respect to time, we have to take the derivative of w squared with respect to itself. We'll get 2w, and then we're going to multiply by dw dt. So now plugging into this equation, as I mentioned before, we do have 0.8, and we know that 0.8 is dB by dt. So I have that, but notice how now this equation is dependent upon where we are in time. What is B and what is W at particular points in time? So this will change depending upon how long W and B are. So how are we going to find W and B now? Initially, I didn't write all of this down when we first started. At time 0, B was 1.5. dB by dt is 0.8. They're asking me to find dW by dt. And again, as I mentioned, there's the formula we have. Now this formula is dependent upon B and W, and their values, of course, are also dependent upon time. So what's happening? How are we going to figure out what's going on? So the slide rate is 0.8 meters per second. So at 1 second, what should happen? This is where we were initially. So if we take a look at this picture here, initially, how far away were we? This was 1.5 meters from the wall. So that's where we started initially. And now 1 second later, it will have shifted over 0.8. So at 1 second, B is going to be 2.3. So that's where that is coming from. And again, this is the point at time at which they want us to make this calculation. Now, how am I going to find W? I'm going to use the Pythagorean theorem. So 5 squared is 1.5 squared plus W squared. That gives me W would be the square root of 5 squared minus 1.5 squared, and that's approximately 4.4. So now what does that mean? Plugging into the formula now, at time 1 second, B is now 2.3. dB dt doesn't depend on time. It's always 0.8. And then I'm going to add 2 times. What is W at 1 second? It's 4.4. And now we're trying to find dW by dt. So I'm going to isolate this equation for dW by dt. So 2 times 2.3 times 0.8 is 3.68. 2 times 4.4 is 8.8. So this becomes 0 equals 3.68 plus 8.8 dW by dt. I'm going to now isolate. So let's say I bring this over to this side. I'm going to get negative 3.68. Then I'm going to need to divide by 8.8 in order to isolate for dW by dt. So dW by dt is negative 3.68 divided by 8.8, which is approximately, maybe that's exact. No, I got approximate there, 0.42. The reason we have to use approximate is because 4.4 was approximate. So dW by dt is approximately negative 0.42 meters per second. It does pass my reasonableness check. I was expecting it to be negative because as the ladder slides out this way, the base is shifting in that direction. The top is going to be shifting down. And if it's shifting down, we're expecting it to be negative. All right, so that was an example of how related rate problems work. You've got the equation, you differentiate everything with respect to time, and then remember how I mentioned here, do not substitute until you've computed the derivatives. That's what I'm talking about here. The point in time we were interested in was 1 second, and we did not do any substitutions up front here, like plugging in what we thought B and W were. You have to take the derivative first before you plug those in. Otherwise, you're not going to be able to get any rates of change. We do need dB by dt and dW by dt because those are the related rates. And now maybe if we jump back out to here now, perhaps you sort of see the humor in this. So rather than actually doing the algebraic solution, which we did over here, this person has decided that maybe it's just easier to set a ladder up and pull it out at the specific rate and have it drop down and then measure what that happens to be. I'm not convinced that would at all be easier. All right, so now that we've seen the process, again, what's the process? Read the problem carefully. Find a relationship, like do I see a triangle? In this case, we saw a triangle. So we knew we were the Pythagorean theorem. Once you've got that set up, you're going to end up having to take the derivative with respect to time. And then they'll give you some information about what point in time you want to be kept making the calculation for. And you might have to make some side calculations over here. All right, so let's move on to the next problem. So the next problem is talking about water being poured into a fish tank. I'm going to take a look at that. The clue I'm going to get from that cubic meters per minute, this is dV dt. So they've given me a d volume by time. That's a clue that I'm going to need to use a formula for volume. Tells it has a rectangular base that's 2 by 3. So you sort of have this rectangle here, 3 by 2, and you've got a height. That's probably enough to get you started. So set up your formula for the volume of this particular thing. They're not giving you much information, are they? They just, how fast is the water level rising? They're not giving you a point in time. They're not telling you at a specific height. An interesting question would be, why aren't they giving you information like that? So what I'm going to suggest you do is, let's set the problem up, take the derivative, see if you can find the answer without knowing a specific point in time. And what I'm going to do is pause the video just as a reminder that it's actually best if you do the work. Okay, moving forward and taking a look at this. There was my little fish tank here. It's 3 meters by 2 meters. Sort of did a rough sketch on the previous page. I said that the derivative of volume with respect to time was 0.3. They're asking for how fast the water level was rising, so they were asking me to find dH by dt. Because it's a rectangular base prism, volume would be length times width times height, and that's going to give me volume is 2 times 3 times height, and that gives me the formula that volume is 6 times height. So the next thing we're going to do now is take the derivative with respect to time. So taking the derivative of v with respect to time is just going to be dv dt, because the derivative of v with respect to itself is going to be 1, so there's really a 1 times dv dt. The derivative of height with respect to itself was 1. I didn't write it. And then times dh by dt. So this becomes dv over dt equals 6 dh by dt. The related rate change in volume with respect to time was given to us. It's 0.3. 6 times dh dt, or dh by dt. So dh by dt is going to be equal to 0.3 divided by 6, which is 0.05. So the water level is going to be rising at 0.05 meters per minute, regardless of where we are in time. Notice how there was no variable here. In the previous one we had a b and we had a w. So it mattered at what point in time we were. We were going to need to know the b and we were going to need to know the w. But in this particular instance we didn't need to, because it's not dependent upon h or a v value. It's always going to change at 0.05 meters per minute. And again, just summarizing, how are these problems done? They're going to be talking about something. They'll give you a rate, and it'll be clear. In this case, they were talking about volume. Write down that formula, take the derivative with respect to time, and look at sort of the pieces that we're missing. So the next one, again, take a look at this. What is that? That looks like dV by dt to me. So it's volume again. Tells me it's a cone, so I'm going to need the volume of a cone. And in this particular one, I'm going to give you a bit of a hint. So the cone is looking like this. The radius is 4, the height is 10. And then at some point in time, you're going to be over here. It says when we are 5 meters high, so then we're going to hit 5 meters at some point in time, and we're going to be thinking about this triangle. What I want you to notice is that this triangle here is going to be similar to the larger triangle. So the little blue triangle is similar to the smaller triangle. That'll give you a relationship between h and r, which you're going to need, because when you start to take the derivative of this, you'll notice how you're not told anything with respect to how the radius is changing with respect to time, and you are trying to find this, so you're trying to find dh by dt. So if they haven't given you dr by dt, then there must be a way to figure out what dr by dt is, or there must be a way to get rid of r. Again, I'm going to pause now, and just as a reminder, it's best if you actually try to solve these rather than just looking at the solution. Okay, resuming. Just want to make sure I have a thin pen when I jump to the next slide. All right, so let's take this a bit at a time. I did suggest to you that we were going to have similar triangles involved. That here is the whole large cross section. If it was filled to the top, This would be 10, this would be 4, but we're not filling all the way to the top. At that point in time which we stop, I'm going to note here would be H, and it doesn't have to be this 5-meter mark, it's any point in time. So we stop at a specific H. It'll have a specific radius as well. I want you to notice that this larger triangle is similar to the smaller triangle. These two lines are parallel, which means these two angles would have to be equal. Those angles are both 90 and they're sharing this angle here. So they have 3 angles that are equal to each other, so they are definitely similar. Now the definition of similar says that sides would be proportional. So R over H would need to be equal to 4 over 10. That's where that came from. Those two triangles are similar, so R over H is equal to 4 over 10. That gives me 10R equals 4H. And that gives me R is 4/10 of H, or R is 2/5 of H. It is possible at this point in time now to get rid of R in this equation by simply plugging in a 2/5 H, squaring it, and simplifying that. Because anywhere in this cone, that relationship is always going to be true. I took a different stance. I noted that if I take the derivative with respect to both sides of this equation, with respect to time, derivative of both sides, I will get dr dt is equal to 2/5 dh dt. And then I'm going to plug that in later on. They did tell me the point in time I was worried about was 5 meters. So at 5 meters, I'm going to need to know what the radius is. So when h is 5, the radius is going to be 2/5 of h. And 2/5 of 5 is 2. So when h is 5, that implies the radius is 2. And as we noted on the previous slide, this is dv by dt. Whoops, that's dv by dt. And water level rising is dh by dt. So we got all the pieces we need. The formula for volume is 1/3 pi r squared h. I'm now going to have to take the derivative of both sides with respect to t. So I want to do d by dt on all of these pieces. So the left side becomes dv by dt. I'm going to view this as a constant, right? There's the constant. So 1/3 pi times. And now on this piece, it is a product, so I'm going to have to use the product rule. So the derivative of r squared, starting with the r squared piece, with respect to itself is 2r. Times dr by dt, and then I need the h as well. So the derivative of r squared with respect to time is 2r dr by dt, and then I need to times by h. Plus, there's r squared, and now I need to multiply by the derivative of h with respect to time. That's just going to become dh by dt. Notice in our formula now, it is dependent upon r and h. It's dependent on r squared over here, as opposed to this formula where it wasn't. After we took the derivative, it was only dependent upon some related rates, that rate and this rate. Where this particular question is dependent in addition to the rates, I am also going to need to know what r and h are. But thankfully, we've calculated them already. So when h is 5, a 5 will go there. We found that r is 2, so I plugged the 2 in there. That 2 is from there. Now, I did say we were going to have a problem for dr by dt, right? Because they didn't tell us what dr by dt was. But by working in this similar triangle, I was able to find a relationship between r and h, and I took the derivative of that, and I now know that dr by dt is 2/5 dh by dt. So I plugged in for dr by dt 2/5 dh by dt. And then, whoops, I think we got a boo-boo here with this. Just want to move that over a little bit. That should be over there. All right, back to my pen and make sure it didn't change thickness. There we go. So plugging in for dr by dt, 2/5 dh by dt plus, what is r? It's 2. And I need to square that. And then there's my dh by dt. So really it's a plug and crank. Plug in all the numbers from there. And I also need to plug in dv by dt. So what was dv by dt? It was 6. So I plugged in the 6. Now I'm going to cross 6 times 3 is 18. Divide that by pi. I have 18 over pi. 2 times 2 times 5 times 2/5. 2 times 2 times 2 is 8. That is 1. So I now 8 dH by dt. 2 squared is 4, so 4 dH by dt. 8 dH by dt plus 4 dH by dt gives me 12 dH by dt's. And now to isolate for dH by dt, I'm just going to divide by 12. And I get dH by dt is 12, or 18 over 12 pi. That reduces to 3 over 2 pi, so my exact answer is 3 over 2 pi. My approximate answer is 0.48 meters per minute. So hopefully you're sort of getting the hang of these. No need to panic. What's the question talking about? Write that formula out first. You might want to just take the derivative with respect to time just so that you can see what am I going to need. In this particular case, the way I set it up, I could see I was going to need r and I was going to need dr by dt. And then I just went back and was able to calculate those. So one last one to look at. A spy uses a telescope to track a rocket launch vertically from a launch pad 6 kilometers away. At a certain moment, the angle between the telescope and the ground is equal to pi over 3, and it's changing at a rate of 0.9 radians per minute. What's the rocket's velocity at that moment? All right, I'm going to pause. I'm going to suggest you try and draw the diagram first, and then we'll talk about the diagram, and then I'll let you try the solution. All right, so let's sort of discuss the diagram again. Whoops, I want to make sure when I grab a pen. Going to write thin. All right, so what's happening is as this rocket moves higher, this angle is changing, right? Because the telescope is staying static. It's not moving. When the rocket goes higher, then the angle will get steeper. And as the rocket moves even higher, then the angle is going to get even steeper. So it tells us how the angle is changing over time. I'm just going to erase that ink off, just so we can talk about a few more things here. So erasing the ink, now what? We do have a triangle. So what are our choices? Normally when there's a triangle, you would use the Pythagorean theorem, but the problem is that with this triangle is it's completely changing shape. We've got TR moving, it's getting higher, and DH by DT is getting higher, and they really haven't told me anything about TR. TR is not constant. If it was constant, I definitely would have thought Pythagorean theorem. What I'm going to suggest instead, because they're telling you something about the angle and the rate at which the angle is changing, which is 0.9 radians per minute, and they've given you an angle measure, is that it's probably better to use a trig ratio. You might be able to use the Pythagorean theorem, but I think you'd have to do some trig substitutions to get it to work. All right, so that was my hint for you. Think about trig ratios. Again, I'm pausing as a reminder that you should probably pause and finish this one off on your own. Okay, resuming and working through this one, I'm going to use a tangent ratio because this is what I'm interested in. They want dH by dt. They're asking me to find dH by dt. So I do need to use that side. And this is the constant side that's never going to change. It's always going to be 6 kilometers away. So I'm going to use tangent. Tangent is opposite over adjacent. So I'm going to use the tan ratio. Information they gave me. They told me that d theta by dt is 0.9. Again, I'm trying to find dH by dt. Well, does the moment in time matter? Did we need to know that? Well, let's see. So I'm going to take the derivative of this with respect to time. So we want to do a d by dt on this whole equation. That's d by dt. So the derivative of tan is secant squared theta. So it's secant squared theta times d theta by dt is 1/6 dH by dt. I'm viewing that as 1/6 h. So it's 1/6 times dH by dt. So it turns out I did need to know what theta was. Now, over here, did we need the height? I calculated the height, but it turns out we don't need it. So in order to not make useless calculations, then maybe take the derivative first. Notice there is no h here, so I don't need h. But if I wanted to find the h, I would have just said tangent of pi over 3 is equal to h over 6. That gives me 6 times tan of pi over 3 is h. That gives me root 3 was h. But again, the height was not needed because when I took the derivative with respect to time, I did not have an h constant sitting over here, or not an h, or the variable h was not sitting here. So the only thing we need in order to find dh by dt is theta and d theta by dt. So theta is pi over 3, d theta by dt is 0.9. So now cross multiplying, we have 6 secant squared of pi over 3 times 0.9 is dh by dt. The secant of pi over 3 is 2. So I'm going to now need to square that 2. So 2 squared times 6 times 0.9 gives us 21.6. So dH by t is 21.6 kilometers per minute. And so that's interesting. I actually enjoy doing related rate problems. So that gives you sort of an overview on how to do related rates, and the next lesson will be more practice on these sort of in a game format. So hopefully you found this useful. If you made it to the end, once again, thanks for watching, and don't forget to like and subscribe.